Good day to you. My name's Todd Williams. I'm with Jacobs Engineering, and I'm presenting today on the removal and transformation of PFAS from biosolids in a high temperature pyrolysis system, a bench scale evaluation. I have several co-authors, Scott Gricko, Bauman Bani from Jacobs Engineering, and then Andrew Friedenthal and Andrew White of Char Technology Solutions. So the outline of what I've prepared to speak to you about today is PFAS and biosolids, kind of an overview, what the bench scale purpose that we did and how that is set up, provide some testing results, and then some conclusions. So what are PFAS? I think most people have heard about what they are: man-made compounds, no natural occurrence. And so they're used since the 50s in many products. They're heat resistant, oil resistant, water resistant. They're found in the blood of people, animals, fish worldwide. And the properties that they have been used to make are also, make them useful for us, or also result in their persistence in the environment. So why are we concerned about that? Well, the chemistry properties of PFAS are very complicated. Depending on who you what literature you read, there's a suite of more than 4,000 or more than 5,000 compounds that make up PFAS. And these consist of carbon chains of different lengths. They have functional end groups, carboxyl groups, sulfonate groups, and the per is all carbons in the chain that are bonded with fluorine. And the poly are those that have carbons that are bonded, are not all carbons are bonded with fluorine. So the kind of interesting part of the chemistry of properties of PFAS compounds is there are precursors that can transform to stable terminal end products through different processes. So what are the concerns with PFAS? Well, first of all, there's mounting evidence of health concerns and environmental concentrations. These compounds are recalcitrant and persistent, so they stay around for a long time. Precursors are discharged to the wastewater treatment plant and can cause increase across aeration, at least the measured increase of compounds that are measurable. You're really not creating more PFAS compounds, you're just transforming them. The measured PFAS pass through the wastewater treatment plant with limited or no reduction, and a lot of them are retained in the biosolids. So hence we're going to be talking about that aspect today. Here's a little summary of history of what's been published in the literature from the early 2000s to roughly the current day. And you see the concentrations mostly of PFOA and PFAS, the two most commonly talked about and measured PFAS compounds. So you see quite a wide range of concentrations that are out there in the biosolids. We do see a little bit of a trend towards less concentrations, lower concentrations to some extent as we get to more recent analysis. But this is highly variable dependent on what's being discharged to the to the wastewater facility or the water resource recovery facility, and then end up in the biosolids product. This table, as it points out on the bottom, does not include other PFAS and precursors that may be present. So in the regulatory realm, EPA is developing some risk analysis work. I don't have that summarized here, but to suffice it to say that it's going to be next year or the year after that before some of their activities are approaching where they're going to be considering whether PFAS, PFOA in particular, and PFAS are going to be potentially regulated. But in the meantime, states are approaching PFAS and biosolids standards independently. California is currently sampling and testing all of the wastewater facilities and measuring PFAS compounds. Maine's has already initiated a requirement for testing in biosolids products that are used as fertilizer. And Michigan has leveraged their IPP program, their industrial pretreatment program, against water surface quality standards for an interim policy guidance. And that's what it is. It's the levels that I'm showing you here were made effective July 1st of this year. And basically, if you start from the bottom up, if your PFAS concentrations in biosolids in Michigan are less than 50 parts per billion, then normal land application rules apply. If the PFAS or the PFAS concentrations between 50 and 150, you can still land apply, but at a limited application rate of a 1.5 dry ton per acre. If the PFAS is above 150 parts per billion in the state of Michigan, the regulators will not approve land application. So they'll require you to do a couple of things. One is to figure out what else you're going to do with the material, maybe landfill or do something else. And then number two, they're going to ask you to figure out where is the PFAS coming from in the collection system. So Jacobs wanted to look at pyrolysis, as there has been interest in this, for looking at pyrolysis as a potential way to eliminate PFAS in the biosolids. So we wanted to set up a demonstration that not just looks at the char that's produced, but also to look at the other portions of the process that are producing bio oils and pyrogas. So the demonstration project that we set up was run at a couple of different temperatures, 500C and 700C. And we wanted to look at the concentrations, see if we could close a mass balance at least to assess that. And the purpose of that is to really figure out if regulatory drivers that come, what should be done next to destroy PFAS compounds in the biosolids. So we did a test with a dried biosolids product that was a Class A exceptional quality biosolids material, had been thermally dried to 95% total solids. It was dewatered with belt filter press before that. It was a non-digested sludge. Kind of reading from the bottom up here, but this is the sample of the product, what it looks like. And it's a very effective marketed product that's sold to farmers and is quite a good quality product. So we set up a bench scale to test some of this material in this arrangement. So we had a feed hopper that was purged with nitrogen. We had a mechanical mixer to take that material in that from the pyrolysis chamber and go through that mechanical mixer. We got char out the bottom. Then we had gas coming off the top, going through a condenser that captured any oil that might have been in that off gas. And then we had an exhaust sample. So these were showing you the sample locations of the material. Now, what did this look like? We took 500 grams of dried biosolids feed, continuously fed through this bench scale pyrolysis kiln unit. The study was completed in an independent Western University Institute for Chemicals and Fuels from Alternative Resources in Ontario. The biosolids, as I mentioned, were previously dewatered and dried. And the pyrolysis reactor, as you see in this figure, was operated for 20 minutes at different temperatures. The sampling trains and analytical methods that we used, we did the third-party testing of the gas. This was the most challenging part of sampling and testing. And so we also looked at the proximate and ultimate analysis, the ash characterization, and the calorific value of the char. And these were the methods that were used for the gas, as you see here, and also for the solids. And this is the setup that you see in the photos, the gas sampling train and the analytical equipment. So here is a photo of the pyrolysis feed, the dry biosolids on the left, the oil that was captured in the middle, and the char that resulted from the pyrolysis process. So you can see significant reduction in the amount of material after pyrolysis. So the testing results and analysis, this slide summarizes the composition of byproducts at both temperatures that were tested. On the left is the 500 C and on the right is the 700 C. So what you see from this pie chart is that the amount of char is greater at 40% at the 500 C and it's less at 700 C. The amount of pygas greatly increases between the 500 C and the 700 C. So you get almost twice as much pygas, which is an important aspect. So depending on someone's interest, whether to look at energy production from the pygas or the amount of char that's produced, you would operate at maybe a different temperature for whatever those outputs that you're wanting to see. So this slide summarizes the PFAS testing results that were determined on these 500 grams of dried biosolids. The red circle shows the quantity, the mass in grams of the biosolids that was fed. And if you go horizontally across, you see the char is 200 grams, the gas was 100 grams, and the oil was 200 grams at the 500 C temperature. And if you go to the right, you see at 700 C, the amount of char reduces, the amount of gas, pygas goes up significantly, and the amount of oil decreases. So you get more gas at the higher temperature, as I said before. What you see on the left is the PFAS compounds that were measured in at least one sample and at least one of the different outputs from the process. So there were 24 to 29 compounds that were measured in the different media, but if they weren't measured, we're not showing them here. What you see at the bottom is the amount, the total amount in micrograms of measured PFAS in the biosolids that was fed. And if you look across the bottom, you'll see the quantities that showed up. I'm going to show you this graphically next in two different ways. The first graphic here shows the relative weight in a percentage basis of the different PFAS compounds that were measured. So in the biosolids feedstock, PFAS was the predominant type of material, was a predominant compound that was measured. And then you can see these etfosa and the mefosa and the other compounds that are lesser quantity. On the right, you see the PFAS compounds that came out in the char, and this is just on a percentage basis. These are, so what you see is PFHXS is the largest compound, followed by HXA and PFOA. So the PFAS is not measured. It's not present. This is in the char. If you go to the bottom slide on the left, what's left in the pyrogas is the PFHXA. So that shows up in both the char and the gas. But again, we're not seeing the PFAS in either one of these instances. And if you go to the slide, to the quadrant down on the right bottom, you find at the higher temperature, this PFHXA becomes a smaller component of the remaining mass that's in there. There's a bunch of compounds that are measured, but these are quite small. This slide shows you the relative concentrations. On the left, you see the biosolids. We measure a few different compounds. you saw on the previous slide, PFAS being the biggest concentration at 26 micrograms per kilogram on a dry weight, or parts per billion. You see all the compounds that were measured listed on the right, but only about, I think 6 or 7, maybe 8 compounds showed up in the solids. And then in the char at the 500C, we see just a trace that shows up, less than half a part per billion of a couple of compounds. At 700C, we don't see any measurable PFAS compounds in the char. We don't see any in the oil at either temperature, but we do see a little bit in the pyrogas. If you go to the slide on the right, you see the percentages of destruction that was achieved at the 2 temperatures. Looking at the entire mass, we had 84% reduction at the 500C and 95 to 96% reduction that of the PFAS compounds at the 700 degrees C temperature. So this is good news. We're seeing destruction of the material on an overall mass basis through the system. Now, besides the fact that we're interested in PFAS, we wanted to look at the biochar and the oil, the residues that were remaining, and to make sure that we don't have a problem with metals from an EPA exceptional quality sealing concentration. So we analyzed that. And what you do find is an increase of all the metal contents between the biosolids and the char or the oil. You do see a concentrating effect for most of the compounds, except for arsenic, oddly enough, but also mercury. Those will drop, but the rest of the compounds increase. So we want to make sure that they don't increase to the point that we're causing a potential concern, and we're certainly way below the EPA concentration ceilings. We also looked at the elemental analysis from the standpoint of the feedstock, the char, and its potential fuel value, and the amount of ash that's in there, so that those, if that information is available, should the product be potentially used in an energy, as an energy source or something of that nature. We didn't do analysis further on the biogas. Most of the use of the biogas in a pyrolysis system would be used to fire that pyrolysis system to heat it up to these temperatures. And from that process, you would most likely destroy any of the PFAS compounds that are remaining. So the conclusions from this study was that we measured the mass of PFAS through all of the medium. We found an 84% reduction in PFAS at the 500C temperature, almost a 95 to 96% reduction at 700C. And so on a mass basis, the measured detectable PFAS in the solid side of the char by itself was almost 99% at 500 degrees C and completely below detection levels at 700 C. So this is, again, good news that if one were to apply pyrolysis, we get destruction of the pyrolysis or removal of it from the char, and it appears we get reduction in the 85 to 95% level across the board of all the outputs. It's interesting to note that some compounds not detected in the biosolids showed up as measurable in the gas. So there might be some concentrating or some transformation of precursor compounds. But again, if we're burning that pygas as a fuel source for pyrolysis or for other uses within a plant, that may not be a problem because of it would be destroyed if it's burned at a higher temperature, maybe 1,000 degrees C. And that combustion system might be paired with air pollution control technology in the back end so that you have complete removal of PFAS at least on the measurable side, from all of the outputs. The metal concentrations, as I pointed out in the biosolids, can increase in the resulting biochar. So it's important to look at what those are if somebody's considering this before they go down this path. And we're looking to do more testing on biosolids products that might have higher PFAS concentrations in the future. But I think this is the first test that's a comprehensive look that we're aware of across the board. So it's good news, more to come. I think at this point, that's what I have for the presentation. Be glad to address questions. Thanks very much, and look forward to wrapping that up.